Okay, so finally we are at the point where we can define the real numbers. We can uh, define what's a candidate for the real numbers. And then the task will be to show that it has the properties we want of this construction. So the definition in the book corresponds to, well, the definition we want is definition 8.6.3. And so we're going to define the real numbers we're going to denote it R, with familiar symbol, to be the set of all cuts in Q. Okay, so it's the real numbers will correspond to every real number will correspond to a subset of Q. So you see that the rational numbers are in principle way bigger than Q. You know, the power set, if you remember, I mean, if from 279 perhaps, the cardinality of the power set is, I mean, for finite sets, I mean, it's much bigger, it's 2 to the n, to the cardinality of the set. And in general, if you consider set A, the power set has a different cardinality. Of course, the real numbers are not, well, the real numbers need not correspond to all the subsets of the rational numbers. In fact, they are not. So the set may not be as large as that. But it is, I mean, you can show, I mean, I don't know if you did that in 279 or not, but it can be shown that the cardinality of R is bigger than that of Q, which happens to be in turn equal to the cardinality of the natural numbers. Okay, but after the regression, I mean, we see, I mean, how everything is falling into place. Even the cardinality we expect is different. So we need to fill a lot of holes here for the rational numbers. And well, the thing is that now the task that now, as I said, is to identify the elements in Q with certain cuts with certain cuts in Q, and we need to define some operations and some multiplications that will correspond to what we expect. I mean. So we expect numbers to behave in a certain way, I mean at least the rational numbers, and so the extension should behave in the same way. I mean, and to preserve this, preserve the order already in place in Q. And so when we're doing this, I mean, we'll be very careful. Some of the things will be left to you as exercises, as part of your homework. But the important thing is to have an idea of how things work. So what are the properties that we want? Properties of R that we want. Remember that at this point, the symbol R does not correspond to your usual R, but some set that we just constructed, so the one over here. And we want to show that this set, which corresponds to all the Dedekind cuts, satisfies the usual properties that we've been used to when we work with real numbers. So this is the important part. So properties of real numbers we want. So now we want actually the field and order properties so there are structural things that we want to preserve when we enlarge the rational numbers. I'll remind you some things that you take for granted every day when you do arithmetic, even with real numbers. So, what is the notion of a field? A set F is a field. This again is the set of properties that are summarized in 8.6.4 that you want a set F to satisfy with which is what Q already has. Set F is a field if there are two operations plus minus, plus and times such that the following conditions hold. So both, here these are just placeholders for other operations. I could have called it star and star 1 and star 2. So if you take an algebra, you'll know what I mean. So both, the first property is both plus and the product are commutative. And so that means x plus y is equal to y plus x, and that x times y is equal to y times x. The property of 2 is associativity, so we know that x plus y plus z is the same as x plus y plus z, and the same holds for the product. Okay, so this is associativity of both operations. We want this set F to correspond to a ring. So in that case, we want to, so far, the number 0 satisfies that with plus and the product, this operation is commutative and associative for both the product and the plus. So we wanted to make a difference between two elements that correspond to different identities. So to force our set F to have at least two elements to be a genuine, a genuinely interesting object to look at. So here we want there are two elements, 1 and 0, so 0 and 1. Just keep in mind this is notation. This is just notation. In general, this need not correspond to 0, the number 0 or the number 1. It's just that it's convenient because since we call one of the operations plus and the other one times, it is easier for us to understand this by naming the identity element 0, which is what we're used to. But these are just this is just notation for the two identities. You could have called it E1 or E2 if I wanted to, but it might complicate things. So just keep that in mind for now. And what are the properties that we wanted these identities. First, the thing that I ask you to pay attention to first is that we want these two elements to be different, and 0 plus x is to be equal to x for every x, and 1 times x is to be equal to x times 1 must be, well, this is completely necessary because of commutativity already, and this holds for every x. Four is a property that inverses exist for plus and times, but for the product operation we only require that all non-zero elements are invertible. That is, if x is different from 0, then it implies that there exists a y such that y times x is equal to 1. And we denote y as to be x minus 1 in that case. Similarly, if y is such that y plus x is equal to 0, we denote y minus x. And this is just notation, and I mean we use this notation because that's where we are used to. And finally, the last property. I mean, all these properties we have talked about the plus and the operation times and the product separately. So we need a relation between the two of them, something that relates to operations. That's property F5, which is the all familiar so let me just write it first. So, for all x, y, z in F, well, let's just write it like this. So x times y plus z is equal to x times y plus x times z. Okay. And this is just no need to make a big fuss about it. So this is the distributive property. Okay. One thing that is asked of you in exercise 8.6.3 is to check using the usual operations of addition and multiplication whether the set of natural numbers, set of integers, and the set of rational numbers are in fact fields. Of course, I mean, we've already talked about Q being a field, so this should come as no surprise. But you need to show that that is the case, and show why not for the other two if you think they are not. And one important comment is that we have the cancellation property when we're dealing with fields. So if you have that, so all the operations, like when you subtract the same number on both sides of an inequality, then you can do that and obtain the remainders on both sides. Okay, so that's what has to do with the algebraic properties of the set. So we want R to also have these properties F1 through F5. Q has it. We want the real numbers to have them, and but we also want something else, which is another important property of Q, which is the order. There's an order in place for the rational numbers. Notion of what's bigger and what's smaller. And we also know that all the numbers in the rational, so all the numbers in Q can be compared with each other. And so that's what leads us to this definition. This is 8.6.5. So an ordering on a set F, we're thinking about our field, it is a relation we're going to denote it just like the usual less than or equal to sign, but keep in mind this need not correspond to the usual less than or equal to. And in fact, when we need to define this order for the real numbers that we just constructed, so it will not correspond to the usual notion because the real numbers did not even exist. So the new kind of order needs to be put in place. But we'll say the same notation. We'll use the same notation for the real numbers because we're already familiar with it. So this relation must satisfy the following properties. First one, called ordering 1, is that all sets can be compared. I mean, all sets, all elements can be compared with any other element of the set. So for all x and y in F, one has that x is less than or equal to y, or y is less than or equal to x. So one of the two statements is true. So if we, as a self, is x less than or equal to y, and that's false, then y must be less than or equal to x. Okay? So all elements can be compared to one another. So now the second property is that if you know that one element is not bigger than the other, and you can say the same thing, reversing the roles of y and x, then that implies that both numbers or both elements are the same. And then the very desirable property that if something, I mean, again, we're just using this as a way of finding an intuition behind everything. But so if something is, so if x is smaller than some y, and y is smaller than some z, then we want to say, of course, that then z is greater than or equal to x. X has to be smaller than the even bigger than 1. But remember, this is not for free, and we have to check these properties whenever we are given a definition of an order, because it needs not denote what we were thinking about. And so this is just a notation again. I mean, just don't forget this is just notation that is very familiar to us. And it's because what we have in mind is to actually use it for a candidate for the real numbers. Now, one thing is that one remark we want to make at this point is that when we write x, when x is less than y, we mean by that we have that x is less than or equal to y according to the defined order, but x is not equal to y. Okay. So we don't want x to be equal to y, and since it's smaller than or equal to y, then it must be smaller than that. But this is just a notation again. So we're using the notation of strict inequality when we have this, and we also have the fact that x is not equal to y. Okay, again, new notation. And okay, so another thing that we want for f to be an order field, if f is endowed with an ordering, we denote it denoted the usual less than or equal sign, that satisfies, in addition to the above properties, these are properties that refer to an order. Now we want some things that are compatible with the structure, the algebraic structure of the operations. I mean, here in the definition of order, there are no operations because the set need not be a field. But since we want an order field, we want some extra properties that now involve. I mean, we want some certain statements to be true that involve both the ordering and the operations. Okay, so there's an interplay in all of these things. So the ordering and the operation. So if y is less than or equal to z, then we want that if we add, these are the traditional operations that I was referring to. Then if we add x on both sides, then we keep the inequality as it is. And this is the property 5 that I referred to in previous videos. I said that we're going to assume it for that time, for the time being, but we're going to mention where it comes from. And this is actually a property of any ordered field, and the rational numbers are an ordered field. The rational number of the set Q is an ordered field. So x greater than or equal to 0 and y is also greater than or equal to 0, then if you take the product of the two, then that's also greater than or equal to 0. So remember that actually we use something we used before. So from here, or from this, so from these two properties, instead of writing them from 2, can deduce, for example, that if x is less than y and z is greater than 0, then z times x is less than z times y. So let's make this an observation. And we made use actually of this in an earlier video. And the reason is that, so first of all, by the first property, by the first property for an ordered field, so by 04, we can add -1 on both sides, and we can get that, minus x on both sides, and we get that 0 is less than y minus x. So y minus x is a positive number, and by 05, property 05, since z is positive, then z times y minus x must be greater than 0 as well. But then this implies that, and using the distributive property, c times y minus c times x is greater than 0. Finally, by 04, again, so now we can add z times x on both sides. zy is greater than zx, which is what we wanted. So I'm just being very pedantic here, just to show you that many things that we use every day, and we make use of every day, and we take for granted, can be deduced from these properties. So now we know, that what we did before is actually justified, because the rational numbers, in set Q is an ordered field. So that's all we need. So at this point, we have the properties. We have already listed the properties we want. So we want, first of all, the Dedekind cuts to be a field, to have an ordering, and these two additional properties, 04 and 05, that make it into an order field. But so what's the question now? And this is what you should be thinking about at this point is, so yeah, I mean, so far we just have a set, the set of Dedekind cuts. So we need to define things before checking even these things that this set is an ordered field. We need to define plus, times, and an ordering for the real numbers. And then check that with these R is an order field. Not only that, I mean, there's an extra step actually at the very end, and that is to check that with this definition of R, we can naturally identify Q with some of the elements and some of its elements, and for those elements, the usual operations hold as well. So when we consider this new plus, this new product, and this new ordering, then if two numbers, I mean, if two numbers in Q satisfy that P and Q numbers in Q satisfy that P was less than or equal to Q, then the corresponding set inside the reals, the corresponding sets of P and for P and Q satisfy that they are ordered in the same way for the new order less than or equal that we are about to define. It is over here. And all the properties hold for plus and for the operations of addition and multiplication also. Okay, so this is plenty of material for this module. So we'll do that, and we'll continue then next week with we'll finalize the construction, and we'll proceed into actually doing things with the newly constructed real numbers.